So I've got a new QuickMotion motor, brushless motor, looks like a size 23. This one's for higher voltages. I'm just running on 48 volts here, so I can hit like a couple thousand RPM before I get voltage limited. Maybe this is better with a Xenus compact or an AC powered drive with higher voltage. But they do make 48 volt windings, slightly higher current, lower voltage. They have, some larger and some smaller motors. The cables are pretty cool. Good flex cable. I've got it wired up to a BDL. Maybe next time I'll try this new ACJ that takes BiSS. I believe we can get this motor with a BiSS encoder. And this would be the Xenus compact, and good drive to match with these motors, kind of in the same current range. We'll take a look at the QuickMotion web page. Why did I buy it? Well, it was quick. Like, to get the motor was quick. Good quality motor. 18 months warranty. I mean, this motor, it looks Asian, maybe Korean. It's not Chinese, so maybe we can expect a slightly higher quality. So I took a look for the on the downloads page. You can see the data for the motor. This would be the connection. So the wiring diagram. This one has AA not B, B not, XX not, UVW +5 and ground with a shield. This is the feedback connector. There's various feedback connector options depending on the motor. And of course, UVW and earth to the motor power wires. That was pretty obvious. The wiring, I had connected to the BEL, the 26-pin high density. The wire colors and the shield are called out, and so that was pretty easy to recognize the different colors. There's a nice standard, depending on which motor feedback types you have. Yeah, I see some clock and data options here too. So the motor specifications are on the web page too. That's nice, so I can get all the motor constants. To look up the feedback, I looked up the encoder, and nice construction, 5,000. Oh, that was a Copley drive. That's cool. So I have a 2,500 line or pulses per rev, which is times 4 for 10,000 counts per rev. But there's a absolute encoder, 17-bit, 16-bit multi-turn, resolver option, BiSS. I like that one the best. I'm not sure about this Endat, but we can adapt to it. 2.2 is in the firmware. I'm not sure what ABS is, but maybe it's like a Absolute A or an Icon A format. But these motors do have various windings, so 48 volt windings. I could have got one of those, but I'm using a Xenus drive at the end customer, so that's going to be, 160 volts DC. So that's a good choice. Quick little go through on CME, the basic setup, and brushless rotary. This one has no brake, but there's a brake option. Incremental encoder with Halls, encoder on the motor, of course. We can do encoder loss detection. I put in brake times for coming to a stop and then turning the brake on and holding so we don't drop anything. We don't have a brake here, but it's good for stopping. And I'm in a can open or EtherCAT mode. We can change the mode here and configure the drive, but we'll leave this configured for an EtherCAT master because that's the end goal here. And then, of course, sinusoidal commutation. We'll take a look at the motor specification. So when entering the motor specification, we can gather that from the data. So the motor inertia is 1.9 E minus 10. So I put in 1.9 E minus 1, kilograms centimeters squared. And that puts it in nice values for us. 1.95 of peak, 0.65 continuous torque. The torque constant would be the torque, 0.65, divided by the amps, RMS, 2.6, amps RMS. So this is in units of amps RMS. So 0.25 Newton meters per amps RMS. And I see that value here. I convert it to amps peak, 0.1768 Newton meters per amp peak. They rounded up on this one. That's fine. And then the volts per radians per second, I put the values the same. 1 Newton meter equals 1 volt per radian per second. Check the back EMF. They say 18. Yeah, that's very close. So theoretical top speed, well, if you had 120 volts AC, you could definitely hit 6,000. This says 5,000 for the max rated speed, but the rated speed is 3,000 and that max operating is 5,000. So all the torque at all the rated speed. So I put in 6,000 for the theoretical top speed. I hit calculate to get the initial tuning values, and I saved a motor data file for future use. So that makes it easy to port over to other drives, and just hit calculate. You can see the feedback counts per rev here again. And so for the current loop, we have some current loop tuning, and I got a fault. Feedback error. Let's go back in and turn off the loss detection. Maybe I don't have the index hooked up. Let's turn that off for the moment. Okay. And bandwidth. Yep, there's a fault. Let's see what the fault is. Clear fault. Good, no feedback fault. Maybe I didn't hook up the index here, but we'll take a look at that in a minute. So calculated values, auto-tuning values, human-tuned values should all be about 1 kilohertz. 800 hertz is fine. Let's take a look at the current loop tuning based on the auto setup checkbox. This is small signal current loop tuning. That looks pretty good. And I guess we could use a little bit more integral. So you can see if there's too much proportional gain, you'll start getting some ringing. There's a little bit of a ring there. It's very apparent at 8,000. There you go. Cut it in half. Still a little bit of a ring, perhaps. Maybe I don't need excessive bandwidth here. If the integral is too large, you'll see a bunch of integral windup. So yeah, a little bit of integral windup. Let's knock it down. Still some integral windup. Take it down again. That looks pretty good. So let's see what the current loop bandwidth is. I like about 1 kilohertz, so 800 hertz seems a little low. But it looked like the integral could tweak up a bit. Yeah, 900 hertz. Let's give it a little bit more integral. The bandwidth, the integral proportional. Let's give it more proportional. The integral term tends to give us overshoot, so I don't try to do too much integral. But if you need the bandwidth, and perhaps a little bit more integral. But I'm just going to increase the proportional. Yeah, so good values of current loop tuning. You can see the peak in continuous currents based on the amps peak, not amps RMS. So 2.6 amps RMS times the square root of 2 is 3.68, and then about 3 times that for peak. That looks good. We'll check out the V loop. The calculated value is 3,000. That's actually the rated speed, but that's based on the data that I put in. So I'm going to put in 5,000 for max speed. And I keep getting this warning about, hey, you've only got 48 volts, so you can't really go that fast with 18.5 volts per kRPM, but that's okay. These values here I tuned, but they were calculated pretty close to that. And I moved the pole out to a single pole on the V loop, so 1 pole, 200 hertz. If you have a big inertia, maybe 100 hertz. If you have virtually no inertia, maybe you could push it out to 300 hertz. But let's take a look at the velocity loop tuning. And velocity parameters 100, yeah, that's down from 1,000. I like more like 3 hertz here. Settings tab, yeah, auto setup checkbox still checked. Monitor the current, make sure you don't get current limiting. So, forgot to phase. I'll go back and talk about phasing in a minute here. But let's do 2 hertz. I didn't quite get to the speed I'm commanding. I like to see a nice trapezoidal looking waveform here. Yeah, so we're really zoomed in on the velocity, so that looks good. If the gains are too high in the V loop, VP, you'll start getting buzzing. I moved the pole, so I probably get a little bit more bandwidth out of it, but it's starting to look a little crunchy. Okay, see, double gain gets too high, cut the gain in half. You'll come out of oscillations, and I tweaked the integral term based on settling time in the position loop. But I mean, you could test it here, but it really, adjust it when you're in your position loop. That makes more sense. And I'm going to do a profile move using a trajectory. 2,000 RPM on a 3,000 RPM rated for 160 volts or 120 volts AC is going to be speed limited, so I'm not going to hit 2,000 or 3,000 here, but let's do auto setup checkbox, channel 3, current, actual current, okay. 10,000 is 1 rev. We'll just make a little trajectory move based on some tested values here. And yeah, so the integral looks pretty good. It doesn't overshoot. If you had too much integral, this is what I mean by coming back to the integral when you're doing your position loop tuning, is you can get some overshoot on your, yeah, you see the integral wind up after the move is done. So I dial it back down. If you had a large inertia, you could cut the PP down. Inertia, matched inertia, maybe 1,000 is good. Twice, 10 times, maybe cut this down to 100. And I'm going to do 10 revs here to make sure I can maintain my speed without hitting a voltage limit. Yeah, that's pretty good. Maybe a little bit more integral. I don't want to overdo it or get integral wind up after the move is done. Yeah, that looks pretty tight there. So that's some good tuning. Now, I don't want to forget the phasing, so I'm going to show tools manual phasing, enable, rotate the current vector. You can see the red indicator leads the black needle when you go forward and reverse. When you go forward, counts go up. When you go reverse, counts go down. This has selected VUW and minus 30 degrees. I actually used auto phasing, don't tell anyone. But this phasing looks good. If you were off by 30 degrees, you would see a lead in one direction and then a lag in the other. It's a little bit subjective, but I see the lag there, so we'll give it minus 30. Should be nicely balanced, forward and reverse. Okay, well, thanks for watching, and I hope you liked the quick servo motor.